SwayamPrabha. Digital India. Educated India.
So, very good morning. So, last week we were looking at the solution to the constant heat flux case, which was extended by Sparrow and Gregg to the basic solution which was done by Polhausen, and the solution which was obtained by Ostrach, later on to the constant heat flux case. And here typically we have to define what is called as a modified Grashof number, because we do not know upfront what the temperature difference is going to be in order to calculate the Grashof number based on delta T. Therefore, we do a simple scaling and convert the delta T in terms of heat flux, which is known. Okay. So, based on that we have defined a modified Grashof number, and if we look at the same similarity variable which Polhausen had used, okay, if you look at the eta equal to x times Grashof number by 4 whole power 1/4. So, if you substitute the modified Grashof number into this, you will find that there is no dependence on x, okay, which cannot be possible because the similarity variable has to be a function of both x and y. And therefore, Sparrow and Gregg modified the definition of eta a little bit. They just introduced to the power 1/5 instead of 1/4, and which is now going to be therefore a function of both x and y. So, we will see with this modified definition of similarity variable whether we try to successfully reduce this into a similarity differential equation. So, before doing that, let us also calculate what is the order of magnitude of the reference velocity. Okay. So, since we start from the basic assumption in the similarity solution that u by u reference is actually a function of eta. So, this is the similarity solution assumption. That means, if you plot a non-dimensional velocity profile, so it should be only a function of eta, correct. So, for this you need to know what the u reference is. So, how do we estimate u reference? So, this is the same way that we did for the constant wall temperature case. So, there we equated the order of power of Grashof number and Reynolds number. So, what did we get there? The Grashof number to the power half is the same order as Reynolds number, correct. So, when we talk about therefore, Reynolds number to the power 1/2, this was 1/4. Okay. So, therefore, wherever we had similarity variable in the original Blasius equation, if you remember, this was y by x Rex power half. This is your Blasius similarity variable. So, we replaced Rex power half with Grashof number to the power 1/4 here. That is how Polhausen started. So, now in the present case, our with the modified Grashof number, we have a modified similarity variable, and now therefore, how do we do the order of magnitude? So, in terms of GR star, how do we equate it? This cannot be the same, because now we have modified our similarity variable to be GR star to the power 1/5. So, only 1/5 should be of the order of magnitude of Rex to the power half, okay, according to the current modification of the definition of similarity variable by Sparrow and Gregg. So, this should be the order of magnitude of your modified Grashof number. Okay. So, now can you please substitute our definition of modified Grashof number, calculate what is the order of magnitude of u reference. Huh? That is f of eta here. We started off with okay, so you used g of eta, okay fine, use g of eta then, and then we integrated g of eta and called that as f of eta, okay fine. Okay, it is a function of eta, that is all it is. So now by equating these two you can find out what is the order of u reference. Tell me in terms of Grashof number, because we have Grashof number here, okay. So you can directly tell me in terms of Grashof number, in terms of modified Grashof number. So what do you get? You get a factor of 5 here outside, Grashof number by 5 raised to the power 2 by 5, right, into nu by x. Is that okay? Right. So this is your u by, this is your u reference. Now we can find out the corresponding transformation of the field from xy to eta by using psi. Okay. Now psi is nothing but integral u dy. So which we will substitute from this as u reference into, we will write this as integral g eta into dy as dy by d eta into d eta. So dy by d eta will take out into d eta, and integral g eta d eta is nothing but what you call as f of eta, it is another function. Okay. Therefore psi is equal to u ref into dy by d eta into f of eta. So we know dy by d eta in terms of Grashof number, and u reference also we have calculated. So substitute and tell me what will be the function psi in terms of Grashof number, the modified Grashof. What is dy by d eta? So xx cancels here, so this gives 5 into Grashof, modified Grashof number by 5, the whole raised to the power 1 by 5 into nu. I will put this nu here. Okay. So therefore once you find out psi, now we know the transformation between, therefore psi, and so this should be multiplied by f of eta. So we know the transformation from xy, the flow field in xy coordinate to eta through the relation between psi and f. Okay. Also we know the basic transformation through the similarity variable. Okay. So, therefore, now we can substitute this into the governing equation, the momentum as well as the energy equation the same way. Substitute for u v du by dx du by dy d square u by dy square, okay, and you will be able to reduce this partial differential equations into similarity equation. So, before doing that also we need to find out the similarity variable for theta. Okay. So, let us assume now theta is a function of eta, but we have to find the right non-dimensionalization here. So, in the constant wall temperature case we use T minus T infinity by or minus T infinity, but in the constant heat flux case we do not know the wall temperature, and therefore, this has to be somehow converted in terms of heat flux again. So, we can again use the Fourier's heat flux to do a scaling. Let us say that this is your T wall, this is your T infinity at the edge of the boundary layer. So, what is this distance? Delta T, this is your thermal boundary layer thickness. Therefore, if you apply the Fourier's law, this will be k times T wall minus T infinity by delta T. So, therefore, we can find a scaling for T wall minus T infinity as q double prime delta T by k. Is that okay? So, now the order of delta T is the same as delta, right. So, we can just substitute this as T minus T infinity by q double prime delta by k. And what is delta now? How do you find out delta? Eta is equal to y by delta, correct. So, therefore, we can find this as dy by d eta, right. So, I am going to replace this as dy by d eta. Okay. So, substitute this in terms of Grashof number. So, therefore, what will be theta of, so this will come out to be T minus T infinity by q wall by k into x to the power 1 by 5. Okay. So, just check the transformation whether you can write it in terms of dy by d eta and tell me. So, rather than writing it out separately like this, I will ask you to substitute directly in terms of Grashof number. So, what is dy by d eta in terms of Grashof number? X into Grashof modified Grashof number the 5 power minus 1 by 5. Okay. So, this is your transformation. Is it clear? So, now you can go ahead, substitute this into the momentum and the energy equations. So, you have u du by dx. Remember the coordinate, this is x is along the plate length and y is perpendicular to that, plus v du by dy is equal to nu e square u by dy square plus g beta into okay. So, where now t minus t infinity is equal to, therefore, t is equal to t infinity plus theta of eta into q wall prime by k to x into modified Grashof number by phi the whole power minus 1 by phi. So, you can substitute for dt by dx as this, you have d theta by, so you have basically dt by dx has functional dependence on x directly and also through theta. Okay. Similarly, when you say dt by dy, it is a function of y only through eta. So, like that you have to substitute for all the terms in the momentum and energy equation. So, your g beta t minus t infinity will be again g beta into q wall by k x into correct. So, your t minus t infinity is resubstituted through this. So, similarly you complete the exercise and I will give you the final solution. So, you will find that this transforms the equations into a similarity ordinary differential equation as a function of only eta. Therefore, the momentum equation becomes d cube f by d eta cube minus 3 times df by d eta the whole square plus 4 f into d square f by d eta square minus theta equal to 0. This is the similarity momentum equation, and the energy equation is d square theta by theta square minus Prandtl number into 4f d theta by plus theta into df d theta equal to 0. Okay, so this is how you finally transform. So, you can try this at home. So, the same way that you did the constant wall temperature case, substitute and eliminate the common terms, and this is the final set of equation that you get. Now, we also have to make sure that the boundary conditions have similarity, that means they should not have dependence on x and y. So, how do we do that? So, we know that the set of flow boundary conditions satisfy that at y equal to 0, that is at eta equal to 0, both u and v are 0, which indicates that df by d eta is equal to 0 and also f is equal to 0, right. And at eta going to infinity, our what should happen? U should approach u 0. Okay. So, it is not like your Blasius case. Okay. So, you should still approach 0. So, therefore, your df by d eta should also be 0 at eta going to infinity. And apart from that, what is the condition on energy equation? At eta equal to 0. So, let us look at eta going to infinity. So, there theta will go to 0. Okay. Now, we need one more condition at eta equal to 0, but we do not know the temperature at the wall. Therefore, for terms of theta we cannot define, but what we know is the heat flux. So, what can you define in terms of d theta by d eta? So, you have to once again perform the conversion. So, at the wall you know minus k dt by, so write this in terms of eta, theta and eta, and therefore tell me what will be the condition for d theta by d eta at the wall. So, what do you get for d theta by d eta? Minus 1. So, therefore, at eta equal to 0, d theta by d eta is equal to minus 1, right. So, you have all the boundary conditions required to solve the ODEs here, and once again you have to use the shooting method. You have to start from the wall, okay, and you need boundary condition at the wall for basically both theta and d theta by d eta, but at wall you have only boundary condition for d theta by d eta. So, you have to therefore guess the value of theta at the wall and then satisfy the value of theta at eta going to infinity, same way the iterative method, okay. So, then you will be able to find the complete solution set, and let me tabulate the final solution. So, naturally once again this is a coupled set of ODEs, you have to solve them simultaneously, and therefore, the flow solution is also a function of Prandtl number. For different values of Prandtl number, you will have therefore d square f by d eta square at eta equal to 0, and what do you have for temperature? Theta at eta equal to 0. So, this will be the part of solution that you get, correct. So, you know d theta by d eta at eta equal to 0. So, you therefore guess theta at eta equal to 0 until you iteratively satisfy the condition that theta at eta going to infinity equal to 0, right. So, for different values of Prandtl number, 0.1, this is 1.6434, this will be 2.7507, Prandtl number of 1, this is 0.721, 1.3574, and Prandtl number of 10, this is 0.306, 0.7644, Prandtl number of 100 is 0.465, 1262. So, these are the different values, okay. So, for a Prandtl number of 1, for example, what was the subsequent value of d square f by d eta square for constant wall temperature case? If you go back approximately, say we had for 0.72, it was 0.676, approximately you can say about 0.68 or 0.69. So, therefore, this case the velocity gradient is slightly marginally higher than the constant wall temperature case, okay. So, since the flow and the temperature fields are strongly coupled, you can see that the velocity gradient is also a function of the boundary condition.
That last value is correct.
It should be point, yeah, okay, I have reversed it, 0.12, yeah, you are right, it cannot increase suddenly, 0.1262, and this should be 0.465, that's correct. It should gradually decrease with increasing Prandtl number. So, now having known theta at eta equal to 0, how do you calculate the Nusselt number? We have to finally derive an expression for Nusselt number as a function of the modified Grashof number and Prandtl number. So, how do we get the expression for local Nusselt number? So, you have once again Hx by k, which is q wall by T wall minus T infinity into x by k. Now, in this case we know what is q wall, but we do not know T wall minus T infinity. Okay. So, therefore, put this in terms of theta at eta equal to 0. Okay. So, our definition of theta is, I will write it again here. So, your theta is equal to T minus T infinity by, and this was Grashof number by phi minus 1 by phi, and we also had x outside. So, from this substitute for T wall minus T infinity, that is nothing but theta at eta equal to 0. So, you simply get this as Grashof number by phi raised to the power 1 by phi into 1 by theta at eta equal to 0, correct. So, corresponding value of, you can again fit a correlation as a function of Prandtl number, and you can substitute for theta equal to 0 as a function of Prandtl number. So, you will get a expression for Nusselt number as a function of Grashof and Prandtl numbers. Okay. So, now what we will do next is to look at approximate solutions. So, these are the two exact solutions possible in natural convection. When you talk about external natural convection, when you talk about internal natural convection, it is in a cavity and so on, you do not have exact solutions. Then before going to numerical full set of numerical solutions, we will also look at approximate methods or the integral solution. Yeah. This is all modified Grashof number, correct. So, all this is star. So, is this the same thing, I am using this expression and putting this Grashof number, this is all modified. So, whenever you talk about constant wall flux case, you have to always use modified Grashof number. Okay. So, next what we will do is look at the constant wall temperature case first and try to derive the approximate or the integral solutions similar to the external forced convection that we did. So, this is something less rigorous than the similarity solutions, and nevertheless they give you a useful solution which is kind of close to the exact solution. So, we will start off with the approximate methods. So, we will only focus right now on constant wall temperature boundary condition. You can do a similar exercise for constant heat flux boundary condition also. Okay. So, let us assume that now the wall temperature is maintained constant, you have gravity acting downward and you have a natural convection boundary layer. Okay. the first point in deriving the approximate method is to derive the integral equations for both momentum and energy. So, let us try to find the integral equations by integrating the momentum equation and the energy equation across the boundary layer. Okay. So, now this solution was done by a person called Square. This is called also square solution. This is approximate method. Now, when we do the square solution, you should understand that once we get the integral equation, what is the next step? We guess the profiles for velocity and temperature, substitute them into the integral equation, convert this into a simple ODE, which we can straight away integrate. Okay. Now, in doing that, we need to know the reference velocity. In the Blasius case, in the flat plate case, external force convection, you know that this is your U infinity, but in the natural convection case, we do not know the U ref. Okay. We do not know precisely U ref. Therefore, what are all the unknowns here? We do not know U ref, and then what is the outcome of solving the momentum integral equation? What do we get? Delta. We get an expression for hydrodynamic boundary layer, and then by solving the energy integral, delta T. So, in your integral equation applied to external forced convection, you have only two unknowns, delta and delta T. Your reference velocity is your free stream velocity there, but now in natural convection we have three unknowns. Okay. Unfortunately, we still have only two equations, two integral equations. So, therefore, what do we do is, in the case of Square, he made a very simple assumption that since we are talking about natural convection for mostly gases, we do not talk about very high Prandtl numbers or very low Prandtl numbers, but for Prandtl numbers approximately around 1. So, it is reasonably safe to make an approximation that delta is equal to delta T. So, finally, we therefore reduce the number of unknowns to the number of equations that we have. Okay. So, this is an approximation that Square makes, but we will see whether this will impact the accuracy of the solution much. Still it will be close to the exact solution. Since we have to solve two equations, we need to only reduce this to two number of unknowns. Okay. And therefore, when we integrate this, irrespective of whether we are integrating the momentum or the energy equation, we will still go from 0 to delta only. Okay. So, all of you can now try converting this into an integral equation. Also, we need to write down the continuity equation. Please do not forget it. We need continuity equation in order to relate the v velocity. Okay. So, this also we will have to integrate. So, I have split the second integral here v du by dy as d by dy as of uv minus u into dv by dy. Okay, I have split the second integral into these two parts. So, therefore, what do you get when you integrate d by dy of uv from between the limit 0 and delta? What happens to this particular integral? 0. Okay. There is no u velocity at y equal to 0 and y equal to delta, right. That knocks away. I can use continuity to write dv by dx as dv by dy as du by dx. So, now I can therefore combine these two terms, right. So, I have 2 times 0 to there should be a plus here. So, I have missed a sign somewhere. Okay. So, this is minus here, right. So, this is plus. Okay. So, therefore, 2 times 0 to delta u du by dx dy, this is equal to nu. When I say du by dy between the limit 0 and delta, what is the value at y equal to delta? 0. Okay. So, this will be therefore minus du by dy at y equal to 0, and the last term will be as it is. You cannot, unless you know the temperature profile, okay, you cannot integrate it. So, we just have to retain this as 0 to delta g beta into dy. Okay. So, this is therefore the momentum integral equation. So, let us call this as your momentum integral equation. Right. So, similarly, if you integrate the energy equation, so you have 0 to delta u dt by dx dy, and the second term can also be split. You can write this as 0 to delta d by dy of Vt dy minus 0 to delta t into dv by dy into dy, which we can use the continuity equation and write it like this. This is equal to alpha times once again dt by dy minus alpha dt by dy at y equal to 0. So, if you integrate this between the limits 0 to delta, what do you get? At y equal to 0, v equal to 0, but at y equal to delta, v is not equal to 0, because we have an entrainment happening at the edge of the boundary layer for the boundary layer to grow. Okay. So, that v at delta is obtained from the continuity equation. So, you can therefore substitute for the continuity here. So, you have 0 to delta u dt by dx dy plus becomes v at delta times t infinity. Okay. So, I am substituting for v of delta as minus integral 0 to delta into du by dx dy into t infinity plus 0 to delta into t du by dx dy. Okay. This is equal to minus dt by 0. So, this can again be reduced to the form which will be d by dx of 0 to delta u of t minus t infinity dy, which is equal to minus alpha dt by dy at y equal to 0. Okay. So, you can again write this as d by dx of ut minus t into du by dx, and that and this will cancel, and therefore, finally, you will have two terms which you can combine it. So, this is the same energy integral like what you got for the external forced convection. Okay. Only the momentum integral is now much simpler, the energy integral remains the same, and even the momentum integral you can just write it, you can take the d by dx term out, you can write it as simply d by dx of u square dy, which will be the same as 2u into du by dx. Okay. So, d by dx of u square dy. So, that now once you substitute the approximate profile for velocity, now this becomes an ordinary differential equation with respect to x. Okay. Similarly, once you substitute the approximate profile for temperature and integrate it, you get a ordinary differential equation. So, you get two equations and two unknowns, one is your reference velocity, the other is your delta. Okay. So, you should understand that in this case we are integrating both between the limits 0 to delta. So, we do not distinguish delta and delta t, right. So, therefore, once we derive the integral equation, we have to make a guess for the approximate profiles of velocity and temperature. Now, what will be the proper guess for velocity? Can we make a linear approximation, because I told you that the peak can occur somewhere in between and again drops to 0. So, we in order to approximate this kind of a curve, what kind of a polynomial should we take? At least we should have a cubic polynomial. Whether we take linear or quadratic cannot predict this maxima here. Okay. So, we have to start off with a cubic velocity profile, and that is what Square did. So, he assumed a cubic velocity profile. However, for temperature he used a quadratic profile, which is not a bad approximation, and so this is where he started off by making an assumption that u by u reference is equal to a plus b into y by delta c into y by delta the whole square plus d into y by delta the whole cube. You can make eta is equal to y by delta. So, this was the cubic assumption. Similarly, for theta, okay, you can say a1 plus b1 into y by delta plus c1 into y by delta square. Okay. So, we will stop here. Tomorrow we will solve the two profiles by writing the boundary conditions down, substitute them into the integral equations and proceed further. Okay.